That's great. It's amazing. So let's shift to let's take it from kind of 10,000 feet to get a little bit closer to ground level here. Um, we over the last year, Hunterian Strongest Hearts have been very focused on a cellular type of data, and I know we don't want to get too far ahead of ourselves on this, but some of that data is going to be things we're talking about in future conversations. We're getting really close to some of that being available for everybody. Let's talk a little bit about kind of the next phase. So we've had a fairly successful phase one of this, and the original plan was phase one was the cellular level, phase two was small mammal, phase three larger mammal slash primate, and then the hope is of course to get to a therapeutic to clinical trials. We're moving now into that small mammal testing phase. What are, and I think this is important, what are the actual goals for small mammal testing, and why is that important? I think anecdotally all of us know that we need to test things before we do them, but maybe you could talk to us a little bit more about just why actually is it so important, and how is that data driving where we're going?
Yeah, absolutely. So, I mean, as you mentioned, the goal is to go from an idea really to a therapeutic in a human. So what we do is we start off small. We basically, get a little bit closer and a little bit closer, and a little bit closer, and along the ways make sure that whatever we're testing works and that it's safe. So, as you mentioned, what we've been working on is doing the cell testing. So those are cells that are growing in a dish in a lab, and either human cells or mouse cells or whatever kinds of cells. And we go in and we correct the mutation. So as we were talking about before, we can do that.
So real quick, if I could just interrupt. So the cells that you're working on, you've already given some of these mutations to, and then you're actually correcting those cells. That's kind of phase one, is to correct those mutations in a lab cellular environment.
So actually, what we're doing is we're doing it in the same place
Gotcha.
where the mutation is. That exactly what you mentioned is the phase that's actually going to be coming up for us next.
Got it. Okay, cool.
And we can talk about that later.
Yep.
So the small mammal thing is, as you said, is a standard part of the research path. Typically, it's rodents, and out of that, usually it's mice.
Right.
One of the reasons why mice are in particular really good for DMD is there's actually a mouse out, a well-known established DMD mouse.
Oh, it's something that occurs naturally in mice as well as in humans. So got it.
Exactly. It was a mouse that people were studying. They saw, what it was, that it looked like it had the phenotype of DMD.
Yep.
They later found out that, yeah, it actually has a mutation in the DMD gene. And so what we do is we take that mouse was identified like in 1977 and has long been established in the research community. So what we do is we take that mouse and then we correct it. And so there's a big step up from going from the cells where we're just, showing that we can target specifically the right regions of the gene, to now showing that, here's a diseased animal that we can now cure and what the levels are.
Right. Living, breathing creature that actually is going to replicate cells, and
Yes.
and the treatment is going to, effectively show, yes, this does or doesn't work the way we expect.
Exactly. And
Yep.
so the two things that we're constantly evaluating, safety and efficacy. Those are the two things, right? How safe out is obviously, self-explanatory. The thing is, we don't want something to be toxic. The other thing is we want it to be efficacious, so we want it to work. We want it to.
Yeah, they're not mutually exclusive, effectively.
Yeah. It shouldn't be.
Yeah. Unfortunately, sometimes it is, but well, so I think you answered my next question, which was, why are we testing on specific small mammals? And just to kind of to recap, because this is actually naturally occurring in these animals, and so we can take animals. I believe some dogs show a similar phenotype to DMD that is present in humans. So rodents, mice, dogs, being able to correct it at those levels gives a really good indication of, okay, if we can do it here, then the, correlation would be that very highly likely we could do it in humans. Is that a fair
Yeah,
summation?
yeah. No, I mean, I think um, it's there's a lot of information that we can get from these studies.
Yep.
Everything from whether or not the actual strategy is working. The great news for something like DMD is that people have shown that this works.
Right.
And people have done things in mice to show that they can cure from DMD. And as you mentioned, there's other models like the dog. There's several dog models. They're all naturally occurring
Yep.
mutations. And people have shown that a CRISPR treatment can effectively cure either a mouse or a dog. The big problem is now getting that to humans, and for reasons that are technical, people have not been able to do that in a way that is safe
Right.
and effective.
Yep.
And that's the really the technology that we have
Right.
allows us to go from that to something that works in humans.
That's right. And then I think, just because we're talking about it, there's actually kind of a next step that you've talked a little bit about with me, which is that you can actually start to do work genetically with things like pigs and other animals to
Mhm.
actually replicate very specific human types of mutations to even take that testing to the next step.
Absolutely. So, like all the mouse and the dogs, as we were talking about, are naturally occurring. They just are born and happen to have a mutation.
Right.
Um, One of the things that CRISPR allows us to do is actually engineer mutations. So it's kind of interesting. So now we're talking about CRISPR as a tool.
Right.
And what we do is we use, in the same way we're sort of manipulating a genome, what we can do is manipulate the genome of an animal, and we can create a mutation that exists in humans in that animal.
Yep.
And then we can treat that animal and have something that's closer to the human, right? So that's an engineered model. As you mentioned, the mini pig is actually a really good example of that, where there's a model that exists. Multiple groups have created models that are exon 51 deletion, for example.
Yep. That's great. So that's kind of where we're going, right? And these are things that, Strongest Hearts, our next phase of fundraising is targeted specifically towards the small mammal phase 2 component. But obviously, if we're going there, there's been some successes, and you feel like this is a worthwhile thing to do. So maybe we could talk just a little bit about what you're seeing so far and some of the successes or data that you have so far in terms of what's gone on in the last 12 months.
Yeah, so the biggest thing that I think is, I think what is the most exciting is that we're not talking about a small subset of either DMD or BMD mutations. So what we've been able to do, and part of the things that we're talking about is we're actually in parallel looking at the vast majority of mutations that affect patients.
Right.
So
When we say we, you mean Hunterian,
Yes.
just to be very clear. Yeah.
Yeah.
Not the royal we,
No.
specifically,
Yeah.
specifically Hunterian.
Specifically Hunterian.
Yep.
It's specifically because of Strongest Hearts. So one of the things that, like, as you know, when we went through this path, the idea was that we want to address the disease
Correct.
as a whole. We want to, like, the goal is to reach the entire community.
Yep.
Normally, that would not really be possible, to be honest. In the world of small molecules, you would have to go out and try and find whatever number of things. It hasn't happened yet, and it's not even clear that that's possible. The reason why we could have that conversation is because of CRISPR, and that allows us to now look at, hey, this is a platform, this is a way to finally address many types of mutations, and particularly in DMD and BMD, things like deletions and duplications, and things that are much more complicated to address than the types of therapeutics that are on the market, at least right now. And a big problem with the things that are on the market right now is both certainly lacking efficacy, and things that are certainly questionable safety-wise as well.
Right.
And so this is really the first opportunity the technology is allowing to address these types of mutations.
That's awesome. So again, just to kind of summate here, you guys have not been looking at, just as you were saying, like an exon 51 or an exon 3. And one of the goals when we started talking, a few years ago about working together was the idea that, yes, of course, my family is directly affected by one mutation and one exon, but the reality is that there's, thousands of people who are affected across this whole range. The data that you've gotten so far, and I know there's more data coming out in the next 30, 60, 90 days, but what you've been able to see so far is that this methodology does in fact work across that broader range as we had discussed, and the cellular data has supported that original hypothesis.
Yeah, so that's the great thing about CRISPR. In some sense, it's actually easy, because if we know that there's a mutation and we know that sort of what the fix is, the result that it works is in some sense not surprising.
Right.
The thing that's surprising
It would be
is that we
surprising
can
if it
do
didn't,
it.
right?
Yeah, well, yeah.
Because theoretically, going back to what you said before, if we know where the problem is, we know what the fix is, you're actually just validating data that you already have in that sense.
Absolutely. The thing
Yeah.
that's surprising, and the thing that I don't get over, is when you see it, even on a daily basis, just in action, right? You see how easily it goes, and it modifies the DNA. I mean, this was the type of thing that, 10 years ago was difficult, if not, not quite impossible, but the technology was not there, and certainly not there in a way that was scalable.
Right.
And then CRISPR comes in, now all of a sudden, you can do this. And here I am 10 years later, and it's still like the type of thing that is unbelievably exciting to see. And, it all makes sense.
Right. Yeah. And to me, and I've talked about this, so going off on a bit of a tangent for a second, but you and I have talked about this before. This actually is all in line with just kind of the original theory of CRISPR that won a Nobel Prize in
Exactly.
2001 and 2009 and so on and so forth, where, now the technology has caught up to the theoretical, and you're able to validate these things in a lab environment much more effectively.
Yeah. Yeah, exactly. So you're talking about like the ways that we've been looking to edit DNA.
Yep.
That starts really like in the early 70s, work done at Hopkins. That's really the first generation of editing. And so we've come a long ways from 1970. The technology was developed, some newer technology came out really in the 2000s. And then CRISPR just revolutionizes that thing. That is in 2012.
Yep.
Is when that comes, and that's the wave that we're seeing now.
Right.
And it's materialized in ways with some of the most fastest developed approved therapeutics ever.
Yep.
So sickle cell is the big example.
Right. I was going to go a little bit off subject there, but I would actually love for you to talk about that.